So thank you very much, and thank you a lot for inviting me to give this presentation. So I will try to share my screen then. So is up? Yeah, now it's. So the presentation today is looking on the possibility to reach 100% circularity of the carbon in plastic using thermochemical conversion processes. And I will have put together the work that I've done in my part of the group of energy technology at Chalmers. So we are a fraction of that group. So looking at today's use of plastic in society, we use fossil ethane, LPG, naphtha as the feedstock mainly. We manufacture it, we use it, and then we come into the end use where we have the disposal or the other part of the waste handling where a small fraction is mechanically recovered, but mostly is disposal or energy recovered. If I look on these, especially in the European areas and especially the north, we have gone from disposal, which is a local environmental problem, where the carbon is stored in the plastics and disposed, controlled or uncontrolled in the nature. And of course, for all the plastics, is this uncontrolled in the nature, something that we have to take very seriously and try to avoid. But when we come into the energy recovery, this was the solution, especially during the 90s and the beginning of the new millennium. But then we transformed the local problem into a global problem as we convert all the fossil feedstock then into CO2 into the atmosphere. So instead of having it locally, we spread it around the globe then. So this is something that we try to want to avoid. And especially if I see this from a historic point of view, the disposal was the big issue, to get rid of the waste and minimize the volume. And then we have this ban in the European Union, which has been implemented, especially in the Nordic regions, where energy recovery is the main thing then. The mechanical recycling is actually quite small, which I will show you later, which is and the mechanical recycling is the main recycling methods. And this has quite a tricky part, because when you take, if you have the quality of the waste here and you have defined fractions here, this is the fractions that all are after, because that you can remelt and use for a lot of products. And here, if you have the product of different qualities here, so you can use them for a big share of the products, which is indicated by the gray area. But if you increase the mechanical recycling, you have to go for waste fraction of lower quality. And then it's less products that you can use them for. And if you go even lower, it's even less fractions. This means that even though that in all the regulations and so on, we drive towards more and more mechanical recycling, it means only that we saturate the use or the product or the feedstock for low quality products. And this is actually starting to be quite a big problem, because a lot of the plastics that is sorted out don't find an end market. So the mechanical recycling has its role, and if you can increase it a lot, of course, it will increase the value of the material during its lifetime. But it will only increase this part a little. And if you're still going on what is done today, then for the energy recovery, it will only decrease that to a small fraction. So going into the recycling methods, usually you divide them into mechanical and chemical. But I will say that it's more preferable to say that you could have them as selective methods where you recycle less than 100% carbon. And this is mechanical, that is solvent methods, because here you need to sort out quite a lot of material, which makes a quite big residue. Even when you do the pyrolysis to naphtha, which has started to become quite popular when you look in the literature, where you take in mainly polyolefins and you crack them, or you not crack them, you pyrolyze them, and then you hydrate them into naphtha that can be used into regular steam crackers. If I look on this for the whole fraction, it means that only a part will be recycled. If you take the pyrolysis for olefins, you will have around 50% that goes from the main feedstock into the end. In that part, you will use the residue here for burning it for the energy. But you can, so you have one part is the recycling, one will be residue, and then you need to add energy into the recycling then. If we're going for a fully circular system, we need to go for a system where you can recover 100%. And here you have two parts. You have the syngas route, and the syngas route, an extreme of that is the CCU route, where you burn everything to carbon dioxide, and then you take in energy in order to regain the carbon dioxide back. What you do is actually you split water and you take hydrogen and CO2, and the most efficient route to do it back to olefins is to take it via methanol and then to methanol to olefins. This is a way that you always can do. So here you can actually recover paint on concrete if you want to. It is coming to energy cost. If you burn a little less, you get into the real gasification where you have the syngas and CO2. Then if you take down the energy need quite a bit, so you go from around 35 to around 50% efficiency here. Then we have another part is that we go for a high temperature pyrolysis. In this way, a temperature range, you actually can optimize to take back as much of the monomers directly. Then you will produce a part of the syngas and your part will go over the CO2 route, and then you have to provide the energy in some way. And this is coming back always how to provide the energy into these methods then. So if I look on what's going on in EU and also especially in Sweden, is the electrification of the industry. And so what you do then is that you will add the energy by renewable energy sources. And by doing that, you can create a circularity of the system. And there are quite a number of ways of doing that. And the extreme is, as I showed you, that burn everything into CO2, take it back via electrolysis. But doing this, it means that you don't add any carbon, and you will also lose carbon into this, which means that you have to combine then the systems. You have to combine the biogenic materials, the paper, the wood, the clothes and so on, and take in it into the system for the carbon atoms. Here you also can have this as an alternative energy source, depending on the balancing. And if you do this and you also extract the carbon dioxide, you can actually create also negative CO2 emission. Looking at this, it looks quite nice then, but how does the balances look like if you look on this from a more like a global scale then? So you can look here on the carbon materials. This is materials in the way that I talk about later, the sawn products from wood, paper, clothes. If you look at the biogenic system and the fossil system, is of course all our plastics and other materials that we produce. So in global, we use a fossil amount of 220 million ton of carbon to produce a little more than 300 megaton of carbon product in the products. In this system, we recycle today a very small fraction actually, and most of it have a linear use and one way through. This is what we talk about always when we talk about material, but actually if you look on the biogenic materials, that is actually bigger. So it's more or less 50% bigger biomass material coming here. And here is the manufacturing where you lose the carbon, and a great part of this is used as energy. All of this carbon that goes out here is from energy, providing energy to the system. The interesting part here is that actually if you take away the recycle today, 24, with the products, you end up with 297. So you actually have the same carbon emitted from the biogenic system for the energy use or leftovers in the forest that you don't use as in the products. So we have the carbon material even in a linear system if we can provide the energy. Then we have the waste, and this is of course what is, I would say, more interesting, is how to use this waste. So this is actually quite a bit more than we are using, and the interesting is that in societies where we have a functional waste handling system, that in most, more or less all Europe and part of the Western world, it means that we collect all this carbon either in the waste, regular waste, or in the waste water. So we have all this carbon collected. So we have the carbon source actually. And this carbon source will be more than enough than providing the products that is today done from the fossil. And even if I look on from the energy balance, one can also see that if one use the energy in that coming from the biomass in the system and into this, it will more or less balance out. So we have a good start here. And if I also see on from all new renewable sources as wind, solar, and other things, and also in if you go to UK or another this kind, you also have the nuclear power plants. That is a possibility. And also, it's come down, as you look on the balance, it's quite a big amount of the carbon that goes into the system that actually is stored. And this is the reason why we really need the carbon here from the biomass system. But we can use the biomass wastes. To provide the energy in a 100% circularity system, we have actually 5 choices. We can have biomass combustion directly, the biomass part of the waste, the CO2 to the atmosphere, and use the trees and so on to create the circularity. If you want to have negative CO2 emissions, that is what you actually need. If you want to follow the Paris Agreement, you can capture the CO2 and send it for storage, so you can have biomass and residue. Or if you want to have the CCU route, you can burn your biomass to have the CO2. You have the oxygen from the electrolysis, the hydrogen in, and you create your carbon. Or you can take the electrolysis directly and just use it as a heat source by burning hydrogen and oxygen, and then you can use regular combustion systems of today. And the third is to develop new now I don't know if you see my I will try this. You use the electricity directly, then I will try to place it here. It will not work. Looking at these alternatives, which one you can choose will be quite dependent on where you are and the available energy sources that you have in hand. But the interesting thing to see here, if you look on polyethylene from waste incineration with CCU using renewable electricity, you end up in efficiency range of 35 to 40%. That is actually the same efficiency when going from pulpwood to paper. So it's quite a good efficiency actually. And if you go from polyethylene with its more advanced general methods as the gasification or the last part where you have the high temperature pyrolysis, you can reach up to more or less 60%. So this is much more efficient actually to produce the plastics in in a circular way than produce new paper or cellulose from pulpwood. So if I go for the optimized system, of course, not everything will go through these general methods. You will have part which is more economically viable to do this mechanical solvent and pyrolysis to naphtha when you have you sort them out. But then you have to have a residue that you have to take back if you want to go for this system then. And this residue need to be recovered by any of these general methods. So what is the balance then if we want to have selective or general methods? How much should we aim for to sort out to recycle via this route? And this you can evaluate actually by from a quite theoretical point of view, but it gives quite an interesting result, because if you sort out plastics and you try to recycle it, you will see that around beyond about 50% is very, very hard, because then you need actually to produce polymers of virgin qualities. And as you go for more and more recycling, the last part that add value into recycling system will increase its cost, and it will be exponentially towards the end here. This means that we can actually draw a line like this, the cost, dependent how much we sort out. But then we have the residue, and the more we sort out, the more costly it will be used to use the general methods to recycle, because you have a lower and lower quality of your feedstock. But the characteristics of the general methods is that everything that goes into the general method will approximately given the same cost. So if you start with having everything to general cost, you will have this cost will go for all the fractions that are of the residue. As you sort out more and more, you will have a slight increase of the cost all the time here. So the total cost for the system to reach 100% circularity will be the part that goes to the selective, which is the light blue area, and the green area is to take back the carbon in with the general methods. This you actually can do a quite simple calculation around, where you linearize the problem. So you have you take this as the cost for the selective methods, where you have a constant A times the fraction you sort out, and then you have the cost for the general methods that you just linearize like this. And if you put in reasonable numbers into the A and B, so you can say that the general methods will increase its cost by around 30% over the residues then that you sort out. And the selective methods will be somewhere between, have an A between somewhere between 3 and 7. And this it's a very, very wide range. But the interesting part here is when you solve this, is that you see that the contribution of the selective methods in relation to converting everything by the general methods will only give around 3 to 8% cost reduction. And this cost reduction will come already when you have a sorting out between 10 and 20%. So this means that the recycling methods that it's put more effort today on will only in a circular system will only be economic to use for around 10 to 20%. 80 to 90% of the recycling, if you go for optimizing from the economic point of view, will have to be done then through these general methods. So does it cost? Is it reasonable to do this? And the CCU case is, of course, the one who gives the boundary, because this we can always do. This is our waste incinerators where you extract the CO2. And here, this route you can get 100% recycling, energy efficiency around 35%. And if you take the example of Sweden, and we have already the waste incinerators in place, we actually only need to extract 70% of the CO2 produced in the waste incinerators to provide all carbon needed for our plastics we use in Sweden. So if we look on this system and we start the circularity, we can also see the fossil part inside of the system will decrease. And after quite a few years, you will actually have everything renewable. And this will be very tricky from the legislation point of view, because today one say that everything that comes in from the chemical industry, this route, it's to seen as a fossil. But if we start with the circularity, we actually will go from take away all the fossil carbon, and at the same time we will have only renewable fraction. Looking at this from a balancing, then we have and the cost. So we will in Sweden will have to take out 1.1 million ton carbon, and we have to provide quite a lot of hydrogen and electricity for the synthesis. But if one put all these together, one will end up with around 1,300 euro per ton olefins. This can be compared with around 900 to 1,000 euro per ton olefins that is today, which means that it will be around 30% more expensive. So you will not see this on the price if you buy plastic products, because this is well inside of the fluctuation over the years of the olefins. So this is quite positive. And if I look on it from an energy point of view, one in Swedish context, you would have needed 30 terawatt hour of electrical power added, and that can be compared to the 160 terawatt hour that is produced at present. So it's reasonable to do, but of course one can go for more efficient methods. And the more efficient method is to optimize the whole system. How much should we actually try to take directly into the building blocks of the different plastic materials? And for those who are interested, we have a paper on this where we also calculate the cost for taking the petrochemical plant in Sweden and replace it then with a steam cracker for plastics to replace all fossil feedstock with recycled. And this also gives the possibility here in the combustion to use what we call the biomass waste and so on to balance the system. So you don't only need to see the electricity, you can also say biomass if you allow CO2 from the biomass to be emitted to the atmosphere. So this is the route where we have our main focus on how to optimize the high temperature pyrolysis to take out as much as monomers as possible, but by keeping the carbon in the system and provide energy in different ways. And I will show you later, our experimental use is to use biomass. So what you do is actually you change the raw material in the steam cracker. And this needs to build new crackers because you cannot take in plastic bags or wood waste into today's plants that is designed and built for liquid or gaseous fuel feedstocks. But in the principle, it's the same. You heat on one side and you provide steam, and you feedstock on the other. You get the gas that you distillate into in the gas chemical factories. This is not really new. Kamensky and others have quite a big share of work on this already in the 80s and 90s. And one can see them from polyethylene and polyphenic mixtures, you actually are getting the same values at the naphtha. And here is the severity of the process and the yield of ethylene, which is usually a measure on how good a cracker process is. And one can see then that the plastic feedstock is equally good. But of course, if you go in for other plastics that is not olefins, you will have a lot of other materials then. And that you can see them from the carbon balance. And when one look on this, and our aim, of course, is to develop a process where we dissolve this and we control the conversion. And for this, we have our own steam cracker or gasifier, which can convert around 5 tons of plastics a day, which is 250,000 plastic bags, which is quite a lot. So it's a 14-meter high combustor unit where we use biomass to heat a gasifier, and we're using a bed material here instead of the wall, which means that we can, taking in the feedstock, it can be charring, and the charring will feed on the bed material, and the bed material will go over to the combustor and burned and used as an energy source, which means that we have regeneration of the walls in the steam cracker all the time by this method. And this is a more detailed, and this is equipped with several hundred or more than 100 measurement tools that we can go into measurement, and several hundred sensors. And it has been used for both development, the fluidized bed combustion technology, later the dual bed gasification, and now we use it for the plastic cracker, where we use biomass here for providing the heat, and we do the plastic on this, where we use the heat from the biomass combustion to convert our plastics into valuable products. Our experimental work has been mainly to see on the feedstock that we are using. One feedstock is the same that you use in pyrolysis where you produce naphtha, which is creating a reference. And then we are looking on feedstock that are lower and lower quality and see how far down it is reasonable to use this feedstock for this type of method where you can create valuable monomers. And this is some example of materials. This is the virgin polyethylene we have used in order to create a reference, but then we have used post-consumer waste of polyethylene and polypropylene, out the shredded residue, which is more or less everything, textile residues, cable plastics with PVC and cross-linked PE and so on. And what we can see is then that dependent on the different feedstock, we can then balance the different outputs. And here, if you compare to the other, which I think that you are not able to do in this fast presentation, but here we are in this slide a little lower, but we have a huge number of controlling parameters, and we know now from the last experiments and so on that we can reach about 50% with polyethylene producing ethylene and propylene, and create more than 70% of good feedstock of BTX and this other. And even all the other gives reasonable feedstock. And our research now is mostly to resolve this, what to say here, the unknown, the blue area, which is the fraction that will be sent around and recycled into the cracker again to produce valuable feedstock, which where you have the monomers in the bottom here, or the Cu and ozone gas in the top, together with mainly the methane, then, which we try to reduce, or in a circular system that will be reformed then into a syngas that also we will taking back through mainly methanol route. These reactors are available. This is the example of the Go Gas plant. This was a nearly 160 million euro investment, demonstrating the biomass into biomethane. The reactor system here, mostly from 1011 here, is actually exactly the same that you will have to use, you would use if you will recycle plastic reuse. So this type of system are up and running or up and industrially shown in the case in the sizes of like 60 to 70,000. So the general conclusion is that in 100% circularity, you will have around 70% or more that will be recycled through this general method that have been shown. The CCU route represents the upper boundary for how much it can cost, and it will be reasonable. Steam cracking of this can make it more efficient, and this type of method are already up in at semi-industrial scale in the development. So thank you very much for this.
Thank you. Thank you very much, Henrik, for your very interesting presentation. A lot of data, a lot of study from my side to digest all of them, but very, very interesting and inspiring. I have personally two very basic questions. So you said that they are, I mean, your studies, they are very interesting study. That steam cracker in Chalmers, 40 meters high, is impressive. You said that you are at the pre-industrial development phase. And my question is, do you think, I mean, how long will it take to become a reality in Sweden? I mean, to be used, if the politics, I mean, the politicians accept it, how long would it take to become, yes, a reality in your country?
If one look on this plant, the Go by gas plant we were looking on and look on the possibility, now it was some other issues that was, then the estimate was that it could be up and running in the 70,000 ton scale in like 2 years.
Wow.
That was the rate. If it was that, if you will build this type of plant from scratch with permits and everything, I would say that it takes 4 to 5 years. But I would say that it's more about the trust from in industry wanting to build it, because the reactor systems are available.
Yeah.
And so it's more that you can see and find economy and someone who believes in it that it would. Yes. But this is the same for a lot of these technologies, and and many of these technologies are on the shelves of bigger manufacturers.
Yes, very interesting. And second, very basic questions. So the exportability of the method, I know that you cannot answer properly because you should know in details the situation in each single country. But how general is this method? For instance, just looking at Europe.
Yeah, the system we want is you have the availability of the biomass if you want to go 100% circularity. And if you don't have a good source of renewable electricity, you can use the biomass on the combustion side. And the balancing in most countries will be that the biomass in the waste streams will be enough. If you are allocated these streams, you will get this system to be self-sustained more or less. So I would say that it's mostly how to allocate the waste streams.
Okay, thank you. Then I see that we have received a question from the attendees. And the question is, I'm reading directly. When you mention pyrolysis, do you mean under inert atmosphere? So this is the first question. Actually, there are two. And the second question is, what do you recommend for recovering the biogas generated besides the biochar? I don't know who asked these questions because there's no name, but these are the questions.
Okay, yeah, the pyrolysis by definition is in inert atmosphere. So you can use either you can use the gas itself or you have the steam, but you need to, especially if you go for the monomers, you have to dilute it. Otherwise, you will start to create a lot of polyaromatics.
Okay.
If you go for the biomass, it's the biochar and so on, here you have a choice if you want to gasify it to the syngas or use it as a fuel on the combustion side to provide the heat for the process. The gas is if you're going for 100% circularity in any of the system, you need to go, part of the feedstock need to go through the syngas route, but by CO and hydrogen or CO2 and hydrogen into methanol and then methanol to olefins. That is the way, and the less of this fraction you need to go through this route, the more economic it will be.
By the way, now I know that Mohamed Chemi from the NRS in Paris asked both questions.
Yeah.
And he's one of the